Okay, today we are going to solve this statics equation. The first thing we can do is we can find the forces on the trapezoidal distributed load. To make this much easier, we will split the trapezoidal distributed load in two. Now, we have a triangle and a rectangle to calculate the force distribution in. So, the rectangle is simply the 3 meters times the 2 Newton meters, which equals 6 newtons of force. The triangle is 1/2 base times height to find our force. We know that our base is 3 meters times height, which in this case is 5 Newton meters minus 2 Newton meters. That is 3 Newton meters. The result is 4.5 newtons of force. The next thing we can do is we can find those force points relative to the, relative to the point C, since we are solving for the forces about C as well as the tension force here. So, what we can do is we know that the center of force about a triangle is 1/3 times the distance, which in this case is 1/3 times 3, which equals 1 meter. However, that would indicate that it is 1 meter away from point A. We want to see in the x direction how far away it is from C. So we can do 3 meters minus 1 meter, which equals 2 meters away from C. The rectangle is much easier. It's just 1/2 times the distance, which equals 1.5 meters. Okay. The next thing we can do is we need to understand the tension force in this point right here. The first thing we can do is calculate the angle relative to the force. So we'll call this theta. As you can see, the run is 2 meters and the rise is 4. We can put this into an equation. Tangent of theta equals run over rise, 2/4. This turns into inverse tangent of 2/4 equals theta. When we put this on our calculator, we find that tangent inverse of 2/4 is 7 degrees. Okay. Now that we have these basic variables, we can plug everything into the a moment equation about C. So we understand that the moment about C should equal 0, since this is a static structure. It is not moving. It has no acceleration or movement of any sort. So now we can plug in all of our values. So first we can, actually let's label these. We'll say 6 newtons is force 1 and 4.5 newtons is force 2. Next, we can say F1 times 6 newtons is 1.5 meters away in the x direction from C. Plus F2, which is 2 meters away from point C in the x direction. Plus, if we look at this structure, we can see that there is a moment force in the counterclockwise direction, CCW. That implies that is a positive. So plus 5 Newton meters. Additionally, we see that there is a 10 Newton force. We can account for this as well by saying plus 10 newtons. Times its height above C, which is 3 meters. 10 times 3. Minus, you can see that all these forces are pointed in a similar direction. That is, to the left. However, the spring force here is resisting that, and it must remain at equilibrium. So, we will say that the force about cable B, or DB, times cosine of our calculated angle, which is 26.57 degrees, minus FDB sine of, oh, we're running out of space here. Let's shift this over a bit. Continuing on, same angle, so 26.57. Times its distance away from C, which for B is 1 in the negative x direction. So, negative 1 meter, and for the D, that is positive 4. Now, we know this equals 0. Okay, now we can simplify. So, we know that F1 is 6 newtons. F2 is 4.5 newtons. Now, if we simplify here, we get 18 plus 5 times 10 times 3, that's 53 newtons, or Newton meters, equals, since we moved over to the positive, over to the equal sign, these become positive. So we have FDB cosine of 26.57 is, excuse me, is 8.84 or 0.894. 0.894, and sine of 26.57 is, we are adding these together, is 1.789. Now, adding those together, we get 2.683. So that means 53 Newton meters equals FDB times 2.683. Now, if we calculate that, we need to divide the 53 by 2.683. And we get approximately 19.75 newtons. And that is our FDB, or essentially the force in this cable right here. The next thing we can do to find the forces about point C is we can sum each of the forces. So first we will find the sum of forces in the x direction, which should equal to 0. So we have Cx minus 10 newtons of force plus our cable forces, which are 19.75 sine of 26.57 degrees. And that's all the x values we have. So set that equal to 0. When we rearrange the equation, we find that Cx equals 10 newtons minus 19.75 sine 26.57 degrees. And that equivalates to 1.17 newtons of force in C of x direction on C of x. Okay, so that's one of our answers. Next, we will find the sum of forces about the y direction, which should also equal 0. So we have C of y minus our distributed load forces, so that is 6 newtons minus 4.5 newtons minus 19.75 cosine of 26.75 or 57, excuse me. Equals 0. Therefore, if we rearrange this equation, Cy equals 10.5 plus 19.75 cosine of 26.57 equals 0. Solving for C of y, we get C of y equals approximately 28.16 newtons. Okay. Now, we have the force on the spring as well as our spring constant, which is given to us initially. In order to find the stretch of the spring, we simply divide the force by the spring constant. So, S, or stretch, equals 19.75 newtons over spring constant of 200 Newton meters. Plugging that into our calculator, we should get 0.09875 meters of stretch. And that's all three answers you're looking for. You have CX, CY, and the stretch.